All right, how's it going? Today I wanted to talk about transformer neural networks. And I think generally these things are fairly simple, but I know that I personally had a lot of trouble understanding them when I first started learning about them. And I think the reason for that is just that the original paper didn't explain them super duper well, in my opinion. So I think that that kind of has had a cascading effect down the line. Um, But yeah, I hope in maybe 10 or 15 minutes here, I can give you just a sort of quick overview of the sort of attention model and how that actually gets packed into the models that we call transformers, things like GPT-3, T5, and so on. There's a lot of famous ones. Um, okay, so let's first talk about just the inductive bias of a transformer. So, any good neural network for a task has something called an inductive bias, which basically means that the network is wired up in such a way that it sort of takes advantage of. Normally, the word people use is symmetry. That it takes advantage of a symmetry of the data or of the problem, the thing that you're trying to model. Um, that usage of the word symmetry may be a little bit of a stretch, but in this case, the thing that the transformer is capturing is that there is information stored in pairwise collections of the data coming in. So I also want to note here that even though the attention layer itself only acts on pairs of the tokens coming in, um, by stacking these layers on top of each other, we do create functions on pairs of elements and pairs of pairs of pairs of elements and so on, even though the inductive bias for a single attention layer is this kind of 2-point function. So a transformer is a sequence model. So it normally works on sequences of vectors. The most classic example is models that do things with free text. So, for instance, a language model predicts the next word given previous words. That's what GPT-3 is. There's also machine translation, is another really popular task where you have a sentence written in English, for instance, and you might want to know what the same sentence mean, or how to write the same sentence in French, for instance. So a sentence is just a sequence of words. So let's do the cat is brown, and I am happy. Let's say that's our sentence. So each of these things, we can talk about how you actually do this later, but you might have a vector that represents each of these objects. And what a attention mechanism does, and more generally a transformer, or I guess less generally a transformer, is to create a function that always looks at pairs of these objects. So it takes really a look at all possible pairs of these tokens, and it uses that to make an inference down the line. So we have this notion of an attention block, and the action of this attention block is to take, again, a list of tokens, a list of vectors, and what it's going to output is another list of vectors, and we're going to get the same number of vectors out here coming out of this attention layer, this attention function, as went in. So there are extra tokens for these. I'm just not drawing them for brevity. So a nice little bit of nomenclature we can add here is let's call these input vectors, the vectors that represent the original words going in, xi, and then we can call the tokens that come out x squiggle I. So this is just to help us remember that each token down here, each token that comes in is going to have a surrogate token that sort of represents the next layer up of information about that input token. So what an attention layer does is it actually computes that. So the attention function is basically all about computing this surrogate token for the input token. And you can stack these things on top of each other. So at the very bottom layer, you might have vectors that represent these words. At the next layer up, you have vectors that represent, some kind of more complete information about the words. And then as you keep going higher and higher, you're continuing to to pack more sort of semantic information into each of these into each of these tokens. Okay, so let's talk about what this function actually is. So the actual attention function is as follows. What you do is for each token xi, you transform it into this surrogate token, like I said, x tilde I. And what this is going to be is it's going to be the sum over all j not equal to I. So the sum over all of the other words of the sum matrix, which I'll call K, acting on xj, times another matrix, which we'll call Q, acting on xi. This is a dot product in here. And then finally, you get a matrix V acting on xj again. And this is the sum on j not equal to I. So another way to say this is that for each token I that we're interested in making the surrogate token for, let me pull purple back. So for each of these tokens I here, which we're interested in calculating the next layer up token for, what we do is we take a matrix Q. This matrix is a learnable parameter. It's one of the things that's being learned or by the model, by the attention layer. We learn Q, and that's just a matrix that multiplies the input token. And we have another matrix here, K, which multiplies the token that we're iterating over. And that gives us what's normally called an attention weight. So we'll call this alpha I j, which is just a scalar. Normally there's actually some normalization factor in here as well, something like root of the number of dimensions for the representation. So one thing that I don't point out until a little bit later, and I think is maybe important to point out here, is that that these alpha ij are also run through a softmax, so that they are normalized such that when you add up all of the alpha I over j, you get 1. So the sum of all the alpha ij over j is equal to 1. And we're going to see later on we're going to do other normalization to this vector. But you can kind of think about this alpha as being kind of a number between 0 and 1. Conceptually, when you're thinking about it, you can just think of this being essentially like a weight that sort of scales how important the context of token j is to the token I. And so if there's a lot of context in j related to I, this alpha should be really large. And if there's not a lot of context between those two tokens, you might expect this alpha to be 0 or really small. Just to give you an example in the sentence here, this word happy has to do with the person I, right? It doesn't have a lot to do with the cat, right? So you might expect that the token for cat is going to have a small attention weight with this word happy here. That may or may not actually be true in a real language model, but just as a sort of conceptual, what could this alpha thing mean, to give you a sort of a way to think about it. It tells you, how much those two tokens have mutual information, or have mutual information is maybe a technical term that I shouldn't be invoking here. But how much context is in between those two words, or those two tokens. Okay. So sometimes, just as a point of order, you'll see this written as something like softmax k q over root k, or something like this, times v. But that is just essentially the same thing as what I've drawn here. Sorry, as I'm saying this, this softmax is not represented in what I've drawn here. So this is just how these weights, these alpha, are normalized. So that's all this softmax is representing, is the fact that these alpha, if you look at the alpha for every other token with respect to the token I, so you're iterating over these tokens j, and you get a different alpha for each of them. Before you do this sum here, what you do is you normalize all of those alpha so that they add to 1, and that's basically what the softmax does. So here, just explicitly, we're showing what the alpha ij are when you include the softmax, and a little tighter representation of the x tilde I. Okay, but conceptually, what you're doing here is you're constructing this weight alpha ij, which tells you it's some scalar that tells you how much the two tokens have sort of mutual context. And once you compute that, you take this vector quantity, which is a transformed version of the vector that you're iterating over j, and you sum up a bunch of those vectors for each j, and the sum that you do is a weighted sum, weighted by this alpha I. So alpha ij. So this is a little bit weird. I think the first time that you see this, especially, I felt this way. I felt very confused by what is going on here. Why would you ever think about this? And I don't think I've ever really found a great explanation for that, honestly. But there is a bit of motivation for why these things are called K, Q, and V, at least. And I can explain that, and it's not a bad thing to see, at least. I think it does kind of help you slightly to remember what's going on here, or why these things are set up the way they are. And a lot of this comes from sort of databases. So suppose you have some data table, right? In your data table, you might have maybe like a users column, you might have like a date column, and you might have some other information, like maybe comment. So this table might be a table that represents like a forum where some user makes a comment at some date, and like maybe there's like a parent in here too, to point to another comment if this is like a reply. So basically, you have this table, and what you would do if you wanted to query this table for information is you would write some, one way you would do this is like in SQL, for instance, you would write a query that says, for instance, if we wanted to get all of the comments posted on January 1st, you might say, select comment from this table where so we wanted to choose something about a day, so we'll say where date equals January 1st, right? So this could be like a query that you write, which comes into this table, and it takes this key here, date, and it looks for some specific information in that key. In this case, it looks for the date to be January 1st. So this is a key. This whole thing is a query. And what you do is you select some information, some value from this table, given that the key has some particular value as well. So that's the basic structure behind the network, or behind the attention layer. And the way that it maps onto that is that, remember what we're doing here is we are creating a surrogate token for some xi. And what we do is we take this, we basically make a query by taking the representation of xi that we have and multiplying it by a matrix Q. And so, another thing I've thought about here, and maybe isn't perfectly obvious, is why use, a matrix transformation here? Why not have like a neural net or something? And, this was just a choice made, I think, in the original paper. I don't have a great, I don't think there's a great reason for that. But, a linear transformation can do a lot of things. It can essentially like slice out bits of this xi vector. It can, create certain simple combinations of the dimensions in xi. So for whatever case, it seems like using a linear transformation to pick out the information from xi to create this query is good enough. It seems to work. This model is extremely successful. So you basically select some information from this xi vector using this matrix multiplication, and that gives you a query. And what you do is you take a dot product between that query and the key value for the other token, the token that you're iterating over. And again, same idea here. This matrix kind of picks out some information from the embedding for that token, xj. And that gives you the sort of relevance of xj to xi for this query. And you then, the value that you look up, once you know how much of that value that you're going to look up by computing this alpha ij, you create, again, a value vector that pulls from the row j some information. So that's the basic idea behind the attention mechanism. Now let's look at transformers in general, or transformers in specific, actually. There's a couple of other things that actually go on besides just attention. So this is kind of like the really famous diagram that you see from the original paper. And I just kind of want to unpack this so we can talk about how this attention layer works in. So that thing that I just described is all of these pink, or I guess these are kind of like peach, maybe orange colored little boxes here. And so let's just go through each of these pieces here and talk about how this whole thing is actually wired up. So first of all, what we have here is an encoder-decoder model. So not all transformers are encoder-decoder. Some of them are decoder only, for instance. A lot of the famous ones, GPT-3, for instance, it's only a decoder. And I'll talk about how the differences there. But for now, let's look at this encoder-decoder architecture. And the basic idea is that you have one type of block over here, which is called an encoder block. And the encoder block has some attention. It also has some other bits to it that I'll describe that are much simpler. We kind of have gotten through the harder part. Like we've gotten through the hardest part already. And what you do is you stack these blocks on top of each other, these encoder blocks, n times. So in this paper, I think they normally have n is equal to 6. Here they have also n decoder blocks. Those numbers don't need to be the same for an encoder-decoder model, but I guess they are in this example. So first you need an input embedding. So one thing I kind of glossed over before was, if you have like the cat is brown, let's just stick with that part of the sentence. How do you actually turn this into a set of tokens? There's a lot of different ways you can do this. One, you can train an embedding using like Word2Vec. Another way is that you can use this trick, which is I think kind of the most common way when you have these kind of like categorical tokens, where you basically just make a hash table. Or I guess I shouldn't call this a hash table. This is not a hash table. This is just a table where you have essentially you put a kind of random vector in here to start. And over time, you allow these to be kind of trainable parameters in your model as well. And that will train you a word embedding from scratch. But ultimately, what you do, normally for NLP, people don't actually use the full word. They use like chunks of the word using something called byte pair encoding. Basically, all that does is reduce the dictionary of words over here so that you have a smaller set of lookups for your tokens. And once you have those these vectors, these are your original word embeddings for your model. Or again, if you're using any other sort of time series, that works too. They don't have to be words, but words are the sort of use case that originally made this model super duper successful. So you have these vectors here, and one thing you need to do, so if you notice what we looked at before, for something like a sentence, it's actually really important where happy is and where cat is, for instance, to know that happy doesn't have to do with cat. Because there's this punctuation here, and I never had the brown. And there's another descriptor here, and there's an I here. So there's all this other information that comes in between. If I had the cat as happy, that would be, of course, more then happy would have a lot to do with the cat. So what you need to do is you need to inform the network somehow, or inform the model somehow, of the order of these words. In this paper, what they do is they use, I forget the name of it, but basically they attach a short vector in front of each of these embeddings. So if I was going to use the word the that comes in the beginning of the sentence, I take this kind of what you might call a positional embedding. And then in addition to that, I sort of just literally tack on the embedding from this table over here next to it. And I have this slightly, longer vector now. And what goes in here in the original paper is some mix of it's like sine plus cosine or something of the position, something like that. I don't totally remember that. This has kind of fallen out of favor to my understanding. What people do now is they just learn these embeddings the same way that I talked about learning the word embeddings. But regardless, there's some positional information that you can put in there. And one way to do it is using these. Each element here is like some sine and cosine with some phase or some different frequency or something like that. So you have the positional embedding, and that's basically what this little box is there. Then what you do with that is you plug it into a attention layer. So this says multi-headed attention. Multi-headed just means that this attention layer that I put here, you can just do this, many times. So for each of these Ks and Qs and Vs, I have, I could basically have many sets of KQV. So I could have K1, K2, Q1, V1, and K2, Q2, V2, right? I could have, n of these. And just run them each independently. So maybe one time when I do this, when I start with a random KQV, I learn certain things about the semantics. When I have a different random setting for KQ and V, I learn like kind of a slightly different set of semantics, and so on. So just like in a convolutional neural net, where you might have at the same layer a bunch of channels of convolutions, you have a bunch of different of just different convolutions going on over the image. You can do the same thing where you have a bunch of different attention layers, or attention heads is kind of the technical term, but that just means that mapping, you just have a. So I also want to note here that the outputs that come out of each attention head are concatenated together. So they're just kind of like stacked horizontally together, and then that is what gets passed into the feed-forward layer. So what you have after that multi-headed attention is this add and norm layer. So which add means just this skip connection here. So skip connection just means that when your vector comes into the model, you go through this attention block, and then when you whatever comes out of this attention block is just then added, literally added, like index by index, they're added to the original vector. So basically this attention head, you can think of it as learning sort of like an additive correction to the original vector. So it doesn't learn a totally new vector, it learns something that you add to the original vector, that sort of perturbation. And then normalization, normally they use a layer norm for this model, or for transformers in general. Layer norm, pretty similar to batch norm. I'm not going to go over it in this video, but essentially it's just a way of making sure that the vectors that come out have a particular have some particular statistics in terms of like their averages and standard deviations, and there's some like scale and bias terms that you learn in there. But basically you just apply sort of a linear transformation to the matrix, or to the vectors that come out, that sort of tries to make the statistics of those vectors a little more well behaved in terms of how much they have spread. Okay, and then each of those tokens go through just a feed-forward layer. So feed-forward layer, most simple sort of neural network that there is. I'm sure everybody knows that if they're watching this video. And again, you have a skip connection and another layer norm step. So remember, out of all of these, what you get again is a bunch of tokens that represent the sequence. Okay, so that's the encoder layer. All right. This is longer than 15 minutes, but that's the way it is. So that's the encoder layer. And then now we're going to jump into the decoder layer. So decoder layer is basically the same thing as the encoder layer, except down here, this is anticipating what's called a sequence-to-sequence model. So it's assuming basically you put in a sequence and then the model outputs a sequence. So this is like a machine translation, is a really common sequence-to-sequence model where you have a string of words going in one language, and you get a string of words coming out in a different language. So these output embeddings would represent the words in the output language. I also want to point out that in some models, for instance, in language models, things like GPT-3, the output embeddings are just the same as the input embeddings, because you're mapping from the same language back into the same language. But this sort of architecture that they're showing here is how you do it when you're doing this kind of encoder decoder your input space is different than your output space. For instance, if we were translating, the cat is brown into French, I don't know, French, le chat something, you would start out by basically putting in a special token, which is called beginning of sentence, and that would be the first token that goes in to the decoder, and then the model would output a token, which might be le, and then you would put in these two tokens, and the model might output another token, shot, right? And then you put in all three of these, and so on. So these output embeddings are just, the output embedding of the sequence. The sequence model, again, there's a positional encoding for each of these. So this would be a position 0. This would be a position 1, position 2. And it goes into the first part of this is essentially the same attention, except for this is just saying during training time, what they do is they mask. So if I was training like a language model, a translation model, I would have, le chat, blah, 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 and I would have the cat is brown. And these would be a training pair for this model. And basically, all it's saying is that when I'm training the decoder, I don't let the decoder see the next tokens. When I ask the decoder, for instance, to predict shot, I am not going to let it see whatever the is brown in French tokens are. Okay, but at inference time, this is the same thing as regular attention. And then there's a kind of special arrow drawn here. So there's a second attention layer in the decoder. And that second attention layer, so then there is one set of tokens coming here. So you can kind of think about this as just like stacking, another attention layer, kind of like we did here, on top of the first attention layer. But there's no feed forward network in between them. And in addition, you are basically taking the keys and the values from the output of the encoder. So I don't actually recall in this paper if each of these n get the output from the final layer of the stack of n, or get the keys and the values, the surrogates from the very top of the stack, or if the first layer gets the first if the first decoder layer gets the outputs from the first encoder layer, and the second decoder layer gets the outputs from the second encoder layer, and so on. I don't actually remember exactly what they do here, but the point is that they essentially do another attention operation here, but for the for K acting on VJ and V acting on VJ, these two vectors, you pull all of them from the encoder side, and then again you do this normalization block. You go through the feed forward layer, and you stack these things some number of times. Ultimately, what comes out goes through just a normal, again, linear feed forward neural network, this one layer, and then through a softmax. So I want to just briefly note on this piece right here. So like I said, the certain really popular transformers are not of this kind. They're decoder only. So for instance, GPT 2 and 3, they actually don't have this piece at all. So that's why I'm kind of glossing over it. Not sure if it's super important for the architecture. I think really, as time has gone on, what we've found is that it's just really this kind of, attention block here that makes this architecture work really well. And that the reason that is super useful is because this sort of inductive bias here, it has this sort of pairwise computation on top of the tokens. So yeah, I think that basically covers pretty much everything I wanted to cover. We kind of got through all the pieces here. In the original transformer paper, we've talked about some simplifications, and we have talked about the attention layer and why the sort of pairwise nature of considering the tokens kind of helps pull out meaningful information from the sequence. So anyway, I think that's it for me today. Thank you guys for watching, and I hope you learned something.